All right, everybody. So in this lesson, we are going to start with a multi-part example, and then we're going to introduce kind of a new idea that continues to develop this one. So we are looking at an investment of $7,000 made at 6.5% annual interest, and this time it's being compounded quarterly. So how long until this investment grows to $10,500? So in keeping with the way that we approached it in our last lesson, I'm going to start with A, P, R, N, and T. So A, in question A, how long until this investment grows to $10,500? We know how much we want this to be worth at the end of however much time. We know how much we started with. We started with $7,000. The rate is 6.5%, which is 0.065. It's compounded quarterly, so N is 4. And in this question, the fact that we see these words, how long until, that tells us that what we don't know is time. So in this problem, we are solving for time, for T. All right, here we go. So we know that A is 10,500, P is 7,000. R over N is 0.065 over 4. And then NT is 4T. So the thing that's really important here, in fact, I'm going to write it in red. In the previous lesson, we did an example, and it was basically plug and chug. It was basically evaluation. Here, we're actually solving an exponential equation. Now, we didn't see any equations identical to this yet, but we've seen equations very similar, and so I'm kind of hoping that looking at this, you realize, I need to isolate the exponential piece and then solve it like by taking a log of both sides. So the first thing we're going to do is we're going to divide both sides by 7,000. Because that 7,000 is keeping the right-hand side from being a pure exponential. So on the right, 10,500 over 7,000 is 1.5. Okay. And now we know that if two things are equal, then their logs must be equal too. So we take the log of both sides. I'm going to take the natural log just because, as I think I've told you all in the past, it's a little bit less writing. And then what I hope you remember from our logs lessons is that by properties of logarithms, the exponent can pop out in front. So we end up with 4t times the natural log of 1 plus 0.065 over 4. And that's equal to the natural log of 1.5. So since we want t by itself, we're going to divide everything off, right? The 4 and the log of 1 plus 0.065 over 4, those are being multiplied by t. So we are going to divide the natural log of 1.5 by 4 times the natural log of 1 plus 0.065 over 4. Now, if someone told you this, if you ask someone, hey, how long until this happens, and they spew this long chain of logs and divisions and all of this, so I obviously need to give you an approximation, but this is the precise answer. So watch in your homework, you will be given instructions for how far to round. Usually it's going to be 3 or 4 decimal places. So I'll do 3. Okay, so here we go. I'm going to punch this into my calculator. So we have 1 plus 0.065 over 4. We're taking the log of that, multiplying it by 4, and then we're dividing the natural log of 1.5 by that. So we have 6 point, and I said I'd round to 3 decimal places, so here I am. Since it's a question about time, we answer it in time. So it'll take approximately 6.288 years. Now, let's move on to part B. Part B is what is the doubling time? And that question is asking us how long will it take for this investment to double? So rather than growing to 10,500, we are now being asked how long until it grows to 14,000. Just for interest's sake, I want you to notice something. In the previous example, 10,500, I specifically made that halfway to doubling. So 10,500, you've increased your original amount by $3,500, which is half of 7,000. So in A, monetarily, you made it halfway to doubling. So you might be thinking, oh, well, if it took like roughly 6.3 years to get to 10,500, wouldn't that mean that it takes 12.6 years or so to get to a double, right? Since you have to grow the same amount of money. So let's keep that in the backs of our heads as we go through this problem. And after we get the final answer, we'll get a chance to talk a little bit about this. Okay, so here goes. From a solving perspective, it's exactly the same. So we have 14,000. We want that to be equal to 7,000 times 1 plus 0.065 over 4 to the power of 4t. Again, this is an exponential equation. So we're going to solve it like an exponential equation. Okay, which means we're going to start by dividing both sides by 7,000. So it actually looks really, really similar, except instead of 1.5, we have 2. Okay, oops. And again, if two things are equal, then their logs must be equal to. So we take the log of both sides. I'm taking natural log, really for no reason. You can take log base 10. You should just use one of the common logs so that you aren't, so that you can actually punch it into a calculator and see the numeric approximation. Just like before, the 4t pops out to the front. And so we end up with the natural log of 2 is equal to 4t times the natural log of 1 plus 0.065. I keep writing 0.05 over 4. And again, since we want t, and t is being multiplied by all this stuff on the right, we're going to divide the natural log of 2 by 4 times the natural log of 1 plus 0.065 over 4. So again, that there is the precise value. But again, if someone asks you how long is this going to take and you spew a bunch of logs and quotients at them, that's not particularly helpful. So let's see what we get here. So let's punch this in. A lot of it is the same work. So if you have a good scientific calculator, you can just sort of reuse everything you wrote here. So we're taking the natural log of 1 plus 0.065 over 4 times 4. And then we're dividing that by we're dividing the natural log of 2 by that. So we have 10.75. I am using 3 decimal places, but the next decimal place is 0. So 10.75 years. So I want you to notice that it took 6.3 years to get halfway to doubling, and then to get from halfway double to all the way double, it took like 4.5 more years. So you can see the rate of increase for the second half of the doubling was actually much higher than the rate of increase for the first half. And this is exponential growth. And if you think back to all of those lessons where we looked at graphs of exponential functions, this is what we were observing. That the climb is fairly gradual at first, but then very quickly gets very, very rapid. Left untamed, exponential growth becomes nearly vertical very, very quickly. So if I were to ask you the question, okay, but what about from here, from 14,000 to 17,500, so another $3,500? It would take even less than it took for the second time. So the second time it took roughly 4.5 years to grow another 3,500. For the next one, it might take just 3 years or just 2.5 years. So with the more time passes, the more it grows. So this really feeds into that narrative of, if you are aiming to save for something like retirement, the earlier you start, the more powerful your contributions, because of this exponential effect. I want to finish this particular conversation looking at a question that really challenges our intuition. What would the doubling time be if we had started with $50,000? So rather than starting with 7,000, we start with 50. So you might find your first instinct to be, well, I mean, you have to grow more money, so obviously it'll take longer, right? So we could even write that down. The instinct might be, it'll take longer. Okay. But let's think about this a little bit. $7,000 earns less interest, money-wise, right? Like if you think about 6.5% of 7,000, that's much smaller than 6.5% of 50,000. So even though you have to make more money to double 50,000 than you have to make to double 7,000, the 50,000 itself is the tool by which you are earning money, and it's earning money faster. So in fact, and I'm going to put ... for now, but look, to double 50,000, you want to grow to 100,000. So if you look at the equation that you would be solving, right, I'm just writing it out exactly as we did in the last example. Let me clean up that weird looking T. Well, the first thing you would do here is you divide both sides by 50,000. That's how we approached the previous two examples. But wait a minute, 100,000 divided by 50,000 is just 2. So you end up with this equation . And if you compare this equation that you're solving for part C is identical to this equation that you were solving for part B. So as it turns out, despite the fact that your instinct might say it would take longer, in fact, it's the same. So doubling time is not affected by how much you started with. Whether you start with $1, $7,000, or $50,000, and you're earning at 6.5% annual interest compounded quarterly, it'll take you 10.75 years to double. So this is compound interest. One of the things that I hope that you have gathered is that compounding itself over time buys us a lot of benefit over simple interest. The number of compoundings is not terribly important, but the fact that it's compounded is what matters. We're going to segue into a new phase of this conversation. And in that phase, we're going to start looking at processes that are a lot less kind of man-made and manufactured than money compounding in bank accounts. So what I want to talk to you about now is I want to talk to you about something called continuous compounding. In the world of money, there are more than this just example, but the example that is really classic for continuous compounding in the world of money is inflation, right? That's actually a fairly complex example. So inflation is the amount that our prices go up over time. So if you look at a gallon of milk, for reasons I don't fully understand, milk is actually one that gets used a lot in the conversation about tracking inflation. If you look at how much your grandparents paid for a quart of milk or a gallon of milk, and you compare it to how much we pay in a quart of milk or a gallon of milk, we pay much, much more. And that's because over time, the value of money goes down, and so prices go up. So you have to spend more money to buy the same thing, which is why it's so important, if you're thinking about long term, that you're investing your money at a rate that is higher than the rate of inflation. Because if you keep your money in like a box, a shoebox underneath your bed or something, it stays like that dollar, you only have that $1. But the amount of stuff that you can buy with that dollar 10 years down the line is actually less than the amount of stuff that you could buy when you first got it. So inflation is an example of something that is continually impacting our prices. There isn't like National Inflation Day. There isn't monthly inflation day when, now it's compounding. So inflation compounds all the time. So what this means from the point of view of A, P, R, N, and T is that N, the number of compounding cycles per year, is infinite. So that brings up the question, right? Like none of us have an infinity button on our calculators. So how do you work it? So what we're going to do is what does 1 plus r over n to the power nt become as n goes to infinity? So we're going to answer this question, but I'm going to start by looking at a simplified version. We're going to make a table. And rather than looking at 1 plus r over n to the power nt, we'll just look at 1 plus 1 over n to the power n. So we'll strip off the r and the t and we'll add them back in later. And I just want to track what happens to this number, 1 plus 1 over n to the power n, as n gets bigger and bigger. So we'll look at n equal to 1, 10, 50, 100, and we'll look at 1,000. Okay, and then we can look beyond that as well. Now, what you might have already started thinking based on our example in the previous lesson where we looked at daily compounding is that there's an asymptotic situation happening, that the bigger n gets, there isn't, like, you don't just grow beyond all bound. You grow a little bit, but there seems to be a ceiling beyond which you'd never go. I hope that that's something that you saw when we went from monthly compounding to daily compounding in the previous example, and we saw almost no change. That's asymptotic behavior. But here we get a chance to see it firsthand. Okay, so I'm plugging in these values of n. So I have 1 plus 1 over 1, which is 1 to the power 1. Okay, so that's 2. Not terribly interesting. Okay, for 10, I have 1 plus 1 over 10 to the 10th power. Okay, so for this we need a calculator. That's 1.1 to the 10th power. So, you know what? I'm actually going to use my squiggly equal sign because it's a long decimal and I'm going to round it. 5.937. Okay, let's look at 50. 1 plus 1 over 50 to the 50th power. Okay, so that's roughly 2.6916. Okay. For n is 100. So we have 1.01 to the 100th power. So that's roughly 2.705. And then we'll do 1,000. If you feel like continuing, please by all means. So we have 1.001 to the 1,000th power. So this is 2.717. Oh, I've been doing 3 decimal places for the last couple. Oh, well. So maybe this isn't reminding you of anything, but maybe it is. A while back when we were talking about logarithms and we introduced common logs, we introduced log, log, which is log base 10. And then we introduced natural log, which we label ln, which is log base e. And at that time I said e is this number, it's the natural exponent. So we'll have a little recall moment. The number e is called the natural exponent. Perhaps a better name for it would be the natural base, but I don't decide the names. And it's approximately equal to 2.718. Okay? So part of the reason that I suggested that if you want to keep going with this chart and add some more values, so look at what happens when when n is 10,000, when n is 100,000, is that I would be interested in seeing you all kind of watch this pattern develop. But I have to stop here for time reasons. And what I want you all to observe is that as n grows beyond all bound, 1 plus 1 over n to the power n goes to e. So in fact, this is why e is called the natural exponent or the natural base, is that when you encounter exponential growth in nature, and a monetary example of that would be inflation, but we'll look at non-monetary examples also, the exponential function that describes that behavior is an exponential function base e. So I will finish this lesson by saying, for continuous compounding, A is equal to P e to the power RT. So gone is all of this, 1 plus R over n to the power NT, and it just becomes e to the power RT. As it turns out, this model doesn't just apply to continuous compounding in the monetary context, it applies to any natural exponential growth. So in our next lesson, we'll look at examples with continuous compounding and then transition to exponential growth and decay in non-monetary settings. Stay tuned.